So in the previous slides, we discussed about the Newton laws actually, and what are the units and each law separately. And let me start today's part with introducing you several forces in real life. Okay, so force is simply defined as a push or pull, right? And you can see in this chart in the we have the diagram force and the important situations, right? If I introduce the push or pull, the simple definition of force, you can make an object accelerate by pushing or pulling, right? Accelerate in the sense you have to introduce velocity difference over a specific time, then it become acceleration. And since force is a vector quantity, you should have a specific direction with, you can denote that by using an arrow. For example, the engine of a car provides the force to push backwards on the road, and frictional forces from the road on the tire push the car forward, right? Friction um, will pull the car, and from the engine to the tire rotation will push the car away, right? That's a simple example. You can see the same scenario in a lifting, and the attraction and repulsion by magnets and electrical charges. Then the self weight, it is starting from the center of gravity of an object to the perfect perpendicular to the Earth's surface. That's called as a weight. Weight is measured in newtons, not in kilograms. If I define that, it is the force of gravity acting on the object. It is usually shown by an arrow pointing vertically downwards from an object's center of gravity. Similar examples, any object in a gravitational field, and it actually less on the moon due to moon's gravity. If you want to, let's say this mass of this object is 5 kilograms, then you have to multiply it by the gravitational acceleration of the g value, which is going to be 10. So if it is 5 kilograms, the weight is 50 newtons, right? Then we'll separately talk about the friction, also another force, right? It is a force that arises when two surfaces rub over one another. For example, you can see it is with this ground and this object. This is the surface. They are rubbing on top of each other, and whenever the friction force actually applied in the opposite direction of the force, if the force is into this direction, then friction is in the other direction. You can see if you are moving an object in this you can see in a slope situation, the object is pushing down and the friction is happening to the opposite side, right? The same can be seen in real scenario when you are pulling an object along the ground, when the vehicles are cornering or sliding down a slope. And there's another force called as a drag. It is similar to the friction. However, drag is happen due to the movement of air, right? When an object moves through the air, there is a friction between the object and the air. Also, the object has to pull aside the air as it moves along. Together, these effects make us the drag, right? When an object moves through the liquid, it also experiences a drag force, right? And you can see car is moving this way due to the air movement. It is dragging the car in this side, right? The similar examples are in aircraft flying, parachuting, or objects falling through air or water, right? The ships sailing. Then we have the upthrust. It is also another lesson actually, right? Upthrust, actually, you can see the weight of an object when it is submerged in water, weight applied in this direction, and there's no reaction for that. According to Newton's third law, for this action of weight, the reaction is upthrust, right? If the upthrust is much higher for light objects, actually, the object is going to float or fully submerged. Any object placed in a fluid such as water or air experience an upward force. This is what make it possible for something to float in water actually. Without any upthrust, you cannot see any object fully submerged or immersed, or it is not going to float. So we will talk about upthrust separately. This can be seen in boats, an iceberg floating, when people swimming, and divers surfacing, a hot air balloon rising. Here you can observe the upthrust. Then we have some contact forces. It is also like a reaction force. Okay. So the weight of an object applied along downwards, and as a reaction for that, you can see from the ground through the center of gravity point of the object, contract force is also immersed. You can see the wall, near the wall the ladder is placed, and from this side there is an action from the ladder to the wall, and as a reaction here we have the contact force. It is also applied from bottom to, from the floor to the ladder as well, right? When you stand on the floor or sit on a chair, there's usually a force that pushes up against your weight and which supports you so that you do not fall down. The contact force is sometimes known as the normal contact force. That is the technical term. We are using the normal contact force or normal force on the of the floor chair, right? Which basically means the perpendicular force, right? Make it 90 degrees from whatever the surface. Uh, as an application, standing on the ground, one object sitting on top of another, and when you are leaning. Then if you have used any kind of a string, right? Strings or ropes, the force term become, the name of the force term is become tension, right? In the strings or rope, we do not say forces, we just say tensions. Okay. This is the force in a rope or a string when it is stretched. If you pull on the ends of an string, it tends to stretch, right? Then the tension forces are arising. The tension in the string pull back against you, right? From here you can see, due to the man's weight, to bottom side, or yes, then the tension arises within the rope too as a reaction force, right? It is acting upwards. It tries to shorten the string, right? And from whatever this string or rope attached on the top, it is also, the string is actually string is also actually pulling that object as well. Pulling this, let's say there's a wood column. That wood column is pulled back by this string. So that is why the tension comes in this direction. So remember, in a string or rope, there are always two tensions meeting each other. You can say the similar scenario when you are stretching a spring as well, right? So as I already explained earlier about the weight, right? It is applying center of gravity to downwards. Right. Again, you can see the difference between a mass and a weight, right? Mass unit is kilograms, the standard unit. For the weight, it is newtons, right? Uh, right. If you look at the summary, the mass of a body is a measure of its resistance to acceleration. You can say that. Also, it is the measure of inertia of a body, and the weight of a body is the force exerted it on its mass by gravity. SI unit for mass is kilograms, weight in newtons. Okay. Then, if I introduce you to the self-adjusting forces, this is separate uh, set of forces actually. As per the name, self-adjusting means when one force is applied, the other force is adjust to that same value, right? For example, if you take one example, let's say if I am pulling an object with 5 newtons, then the resistance also automatically adjusted to 5 newtons. Then if I increase it to 10 newtons, the resistance or the reaction force is also increase up to 10 newtons. Like that, if one variable or force is increased, the other is automatically increased as it is. So this is called as a self-adjusting force. Simply, then let's talk about several self-adjusting forces we have, starting from the tension. So as I told you earlier, tension is occurring within strings and ropes. Okay, consider a piece of rope. This is the rope. which is stretched along. You can see from two hands, the opposite direction, it is stretching, right? So this is the pulling to the right side. This is the pulling force to the left side. And this is the string now, or the rope. These two are the tensions, right? Uh, if I ask what force prevent it from breaking, it is the force called as a tension, which basically means this is one tension. These are the two tensions, right? There, as I told you earlier, there are two tensions acting in the same direction. However, they are similar in value, right? Similar in value. You can see if you, in this case, if it is 10 newtons in this side, right? If this force is 10 newtons, then this tension is also equal to 10 newtons. Now, according to this tension, the right side, so the left side tension is also increased to 10 newtons, right? So if this become 100, this also become 100. If the, and the tension also here, it's also become 100. So it is self-adjustive, right? And what can you find out any other type of force which comes under self-adjusting force category, right? We'll talk about that. There are several of them actually. The first one is the tension actually. If the force is always acting in the rope, it has to be shrinked, right? But it doesn't happen. So this force appears only when it is stretched. When you pull the rope, this force adjusts itself to prevent the breakage of the rope. And when you increase the pulling force, the tension force also will be increased, right? If you increase the pulling, like here, the tension is also increased. So since this tension force adjusts itself, it is called as a self-adjusting force. The opposite of the tension is called as the thrust or compression. And also friction is one of the self-adjusting forces as well. The opposite of the tension is the thrust or compression, right? As you can see in this figure, this acts in a way of opposite to the tension. Now the both hands are compressing the object, right? According to that, these two tensions or compression forces has been uh, happen to exist. This example describes that when you push a small piece of wood by both your hands, a force of compression appears to prevent it from breaking, right? So whatever the force you apply, let's say 20 newtons compression, this automatically become 20 newtons. So that is how this automatic or self-adjusting force work. And this force is changing itself to balance the external force given by the hand. So it is a self-adjusting force. And you can see this is I think banana tree, right? And up to certain days you have to give it a support, right, to prevent it from collapsing. And when the weight of the tree is increasing, what happened? So tension applied by the support is also increasing gradually, right? So this is the thrust force act along the support to prevent the tree from falling. Now we'll talk about the frictional force. Right. Friction force has separate equation. Friction is the force that tries to stop materials sliding across each other. With that being said, right, if I take a now friction happen with the only with the rough surfaces. Okay, you had first of all remember that only with the rough surfaces. For example, let's say I'm taking a, you already know the ground, right? In the ground with the grass, and if you roll a football, right? If you kick some football over the ground, what happened to the ball? At the first case, it is going to increase its high velocity with the acceleration. And over the time, what happened? The ball is definitely going to stop, right? It is not going to uh, always in motion. After certain time, it is going to stop. Now, let's say a player is kicking the ball in this direction, then the friction force applied in the opposite direction through the surfaces start touching with each other, the ball and the ground, right? And remember, you cannot draw a friction force like this. Okay, it is not starting from center of gravity. This is actually starting from the touching surfaces, right? That is the main case. So this ball will eventually stop due to this friction. Friction is also a self-adjusting force up to certain uh, level. It is self-adjusting, which means if you kick the ball with 100 newtons, the friction is also going to be 100 newtons. Then eventually the force will be decreased, right? Uh, if I again move back to more detail in this paragraph, frictional force prevent or opposes relative motion. Uh, Even though we seems to identify most flows like uh, smooth surface. For example, if I look at the carpet road, right? If the carpet road, it seems like very smooth, but microscopically, all surfaces are rough, right? Which means through the carpet roads as well, there is a friction. Even though in the tiles, there is a friction because it seems like smooth, but for our naked eye, we cannot identify the rough spots. And when such two surfaces placed in contact, there will be a region where the irregularities interlocked. Let me show you. Okay, you can see there are two surfaces, right? One is gliding over another, and microscopically you can see there these are the irregularities. Due to these irregularities, the friction is come to life, right? It comes to life. And when these irregularities interlock and points where high pressure may be results in temporary bonds, and any attempt to slide the surface over one another will require a certain amount of work to be done, lifting and deforming the surface. This will require a force as the surface moves. In some circumstances, friction is unwanted because it wastes energy. there are advantages as well as disadvantages of frictional force. I mean, in the households, I mean, if there is no friction, if there's no rough roads, rough surfaces, we cannot even walk actually. We cannot even walk without shoes. With shoes as well as without shoes, we cannot even walk. That is how friction for what this, there are some, we need the friction as well as there are certain cases, for example, in any kind of an engine, any kind of an engine, there are in any kind of engine, there are irregularities, right? Mechanical steel columns and the rotors and the wheels, there are irregularities. So that is why the engines are producing the heat due to that friction. So with the petrol, let's say we are introducing 100 joules. Joules means it's a measure of energy. And due to this friction between the mechanical components and produce of heat, let's say 50 joules will be wasted. So what is the performance of that engine then? It is basically it is limited to 50% or 20%. So it is wasted, right? However, at some circumstances, friction is useful. For example, brake in a car are applied. Okay, when we are braking actually with the disc brake, they are using the friction, right? Is it going to heat then? The brakes are going to be heated. That is a waste, but that there are some advantages. Friction between the wheels and road surface is essential if the car is to be slowed, right? And here are some facts. About 20% of the gasoline used in automobile is needed to counteract friction in the engine and the drivetrain. On the other hand, if the friction totally absent, we could not get an automobile to go anywhere. That is also fact. Or even we couldn't walk or ride a bicycle. What are the other examples? We cannot even, if there's no friction, we cannot hold a pencil with our hands. If we could, it would not write. Because why? It is going to slide away. And the nails and the screws would be useless. Let's say if you are putting a screw somewhere in the wall, but after a certain time, it is going to remove by itself because there's no friction. And the woven cloth will also fall apart, right? Knots of the ropes will also untie. And you can see, remember another thing, friction force direction is opposite to the action force, right? If this is the way, if the object is moving to the right hand side, this is where you can observe the friction. Now with the brief introductions, you can see the irregularities. And here are some examples, right? You can imagine this one actually.